dear students, I'm Meghamala, working assistant professor from Institute of Aeronautical Engineering, EC department. And today I'm going to talk about the problem solving on gate level modeling. Okay, so we will discuss what are the few problems that we come across if you are solving a few problems based on the gate level modeling. So far we have discussed in the module what are the gate levels, what is a gate level modeling. So we know that in the Verilog we have five different types of modeling styles: behavioral modeling, gate level modeling, data flow modeling, and as well as a switch level modeling, right? So now we will discuss about few problems that we come across if you are solving or else in order to develop a particular module in terms of gates, right? So now the first part, it's all about the problem solving in gate level modeling, is about the design of comparator using gates. So now using gates, we will design a few the comparator. The comparator is being designed by using the gates. Now we all know what's a comparator. So comparator is nothing but it is a device. It's an electronic device, or else it is a circuit where it compares the input. For example, in the inputs I have A and B. So however I can compare A and B as inputs, like A is equals to B, A less than B, and A greater than B. So these are the few combinations. So as per the few combinations, I can compare. And it's all about the two input comparator. And likewise, we have 4 input comparator as well. Right? So now we will see a magnitude comparator is a combination circuit. So it's a combination circuit where it compares two digitals or binary numbers. So it will compare two digitals or binary numbers, that is 0, 0, 0, 1, 1, 0. For example, A and B. So 1, 0 and 1, 1. So what am I doing here? I'm comparing. So here I have to compare and finally have to conclude it with the proper output. So here I see A and B as 0. So equals to is achieved. And if it is A is 0 and B is 1, so obviously A is less than B, achieved. And if it is A is 1 and B is 0, A is greater than B, achieved. And finally A is equals to B. So this is how, by using the binary values, we are going to compare the inputs from the inputs with the greater than, less than, or equals to. Then we logically design a circuit with which we will have two inputs. So here we have two inputs, A and B are the two inputs. So as it is an n-bit comparator, we can compare n number of bits. So but however, we are considering here only two A and B as an input, and then the conditions must goes like A greater than B, A is equals to B, and A less than B, right? So these are the conditions. So if your inputs are 0, 0, then A is equals to B is achieved. Okay, based on the inputs and the consideration of the inputs, the numbers, binary values that you are giving to that particular inputs, based on that the output is observed. Then comparator using gates. Now we will see in the problem solving, we will see how the comparators are designed by using the gates. The purpose is to design the simple combination circuit, that is 2-bit comparator. So now we are seeing the purpose is just to design a 2-bit comparator and to gain insights into IC chip minimization instead of gate minimization in implementing the combination circuit. So here we have to know the gain by considering. See, I'm considering a 2-bit comparator, and also to gain the insight of integrated circuit. In order to gain the insights of integrated circuit chip minimization, instead of minimizing the IC, I'm going to minimize the gates. Okay, gate minimization is being done instead of IC chip minimization. Okay, by using the comparator, I can easily minimize the number of gates instead of going for the complex design. Then, now coming to the procedure. In the procedure, during 4 inputs, 3 circuit has been compared to 2-bit unsigned numbers. You can call these numbers as 0, 1, 0 and 1, 0. So here, I'm considering 2 inputs. So for this 2 input, 1 as 0, 1 and 0, and B also 1 and 0. So these are the 2 inputs, right? Then, so here, A1 is the most significant bit of input A. So here for input A1 is the most significant bit. For input B, and A0 is the least significant bit. So A1 is the most significant bit and A0 is the least significant bit. B1 is the most significant bit and B0 is the least significant bit as well. Then now the circuit should have 3 outputs. Why? Because here we are considering the 2 inputs. Then the condition goes it can goes like A is equals to B, A less than B, and A greater than B, right? So here the output will have the indications of the comparisons of the two inputs that we have considered. Then you can label these outputs G, which means A as 1 0, which is greater than B as 1 0, where G stands for greater. Yes, so here we are representing the greater, less and equals to. How is G is for greater, less than is equals to L, and equals to is with the name E, right? Then this is called a comparator circuit. So obviously this is called a comparator circuit where it has two inputs A and B and the three output combinations like G, L and equals to, right? So this is called a comparator circuit because it compares the binary numbers 0 and 1 with the binary inputs A as 1 0, B as 1 0. Now we will see the output should be connected to LED indicator. Okay, why? Because if as per the inputs that I am considering 1 0, so here the output A greater than B, so this LED should glow, right? So the output must be connected to LED indicator. Why? Because if the input I am considering as 1 and 0, it means that A greater than B, A is equals to B, and A less than B. All three combinations will have the LED indicator, but as per the inputs that you are considering and the conditions that you are observing will be given as A greater than B. The LED indicator will glow. By this LED indicator, we can able to say that, okay, so for A as 1, B as 0, A greater than B condition is satisfied. Then note that an output of 1 means the condition being tested by the output is true. So obviously when the output is 1, so here it is 1. If it is 1, that means that output is going to be the true. And if which should turn when it is 1, the LED is on and the condition is going to true, right? If it is 0, LED is off and the condition is going to be false. Okay, this is just for the understanding purpose. Like this is how the mechanism of the comparator goes with when you connect the LED indicator. Then start this problem with a truth table, and that describes the problem. So here in the comparator we have a truth table based on the conditions, based on the inputs and the conditions as well. So here try to minimize the number of IC packages needed. What are we doing here? The main purpose of considering this particular example is, instead of like say we have to minimize IC, right? So we are minimizing IC by minimizing the gate, right? So here chip minimization, to gain insights into IC chip minimization instead of gate minimization. Okay, instead of gate minimization, IC minimization, we are going for easily with the gate minimization. Then one way is with the K-map. One thing is first after considering the input output, we are segregating and we are getting the output based on the LED indicators is one thing. And the second thing is about the K-maps, corner maps, right? So the K-maps, you may be able to further minimize the number of gates by thinking about what these outputs really mean. So here our main purpose is just to minimize the number of gates. For example, in order to construct the comparator using 10 gates, being a designer, I have to consider, or else I have to construct this comparator by using only 5 gates. So how can I minimize this gates? Is one of the best method is going for K-maps, right? So corner maps. Then think about the relationship between the three outputs. So now we have to think about the relationship. If it is A is greater than B, A less than B, and A greater than A is equals to B. So here the minimum number of chips needs is about 5. So here three outputs. The relationship between the three outputs. So for 3 outputs, what are we telling is we need the 5 ICs, right? Then you may get graded down for using more gates than needed. So what happens is as you go on increasing the number of gates, what happens is the degradation of that circuit is observed. So as much as less is the gates, then that much efficient the circuit will be, right? Then always concentrate on reducing the gates instead of increasing the gates. And now we will see the syntax. The syntax of a comparator goes like this. Module is name of a keyword. The name of a circuit is comparator. And here we have A, B greater than, equals to and less than outputs. Inputs are A and B, right? So A is supposed to A as 0 and A as 1. And on the B is supposed to B as 0 and B as 1. And here the condition goes. The condition goes like this: A greater than B, A less than B, and A equals to B. So we have declared input, output, and register greater than, less than, or equals to, right? Then always at the rate. So always at the rate is a keyword meant for the behavioral modeling, right? So in the always at the rate, I am declared A0 or A1 or B0 or B1. It could be either A0 or A1, B0 or B1. Then now we will begin. Here, what I am doing, A1 and A0 is less than B1 and B0. If it is less than, always remember A as 1, B as 0, right? So if it is 1 and 0, if it is 0 and if it is 1, then the condition goes A less than B. So that is what? A less than B. Then goes A greater than B. And if else, if A is less than B, then L. If else, A greater than B, that is greater. Okay. If else, and then it is equals to. Then finally end and then end module. Okay. So here logic equality we are achieving, and sometimes based on the inputs, logic greater than and the logic less than also we are achieving. So this is a syntax where we can compare when the outputs and inputs as 0, when the two inputs in terms of 0, 0, A as 0 and A as 1, B as 0 and B as 1. And now coming to the truth table. So the next thing is, first you just consider the gates which are needed in order to design a circuit, and then go with the truth table, and then go with the K-maps in order to reduce the size of a circuit based on the gates. So here in the truth table, it's a 2-bit comparator, we know. So we have input A1, B1, A1, A and B. So under A is again divided as A1, A0, B as B1 and B0, and then follows with the condition. So now if you observe, A1 and A0 as 0, right? And B1 and B0 as 0. So what sort of condition that we are going to achieve? A equals to B. So then it is nothing but the true. And if it is true, the circuit diagram, the LED will glow, right? LED will be on, right? Then see, for example, A1 as 0 and A0 as 1, right? And then B1 as 1 and B1 as 1. So here the B input has both logic values as 1, whereas A input 1 is 0 and 1 is 1. So 1 bit is less, right? So here in this case, A is less than B. So here A is less than B. This is going to be achieved, and that is nothing but the true. Then when this is true, the LED will glow at A less than B. So likewise here, this is just a truth table where we are designing a 2-bit of macro comparator, and we are going to observe the combinations of based on the input that you are considering. And then after immediately drawing the truth table, let's move forward to the Karnaugh maps. So Karnaugh maps are nothing but the K maps. We can able to draw this K maps based on the truth table. So as per the truth table, here we have segregated A1 and B1, A1, B1, A0, B0. So here 0, 0, 0, 1, 1, 0 and 1, 1. Similarly 0, 0, 0, 1, 1, 0 and as well as 1, 1. So as per this output combinations, or as per this input A0 and A1. So in order to observe this A greater than B. So A greater than B is 1 point is at A1 as 0, right? A1 as 0, A0 as 1. That is 0, 1. So here it is 0, 1, right? So the 0, 1 is 1. And then we are moving, then we got 1 as here. A1 as 1, 0, 1, 0, 0, 0, 1, 0 and 0, 0. So this is, okay. Likewise, based on the ones, how many ones you got as per the condition true, those many ones you have to write at this particular, in the particular K-map. So after drawing K-map, we have to look for the combination. So here how many combinations I can achieve? One quad I'm getting, and one pair I'm getting, right? And one more pair I can get. So totally 2 pairs and 1 quad. So from here, I'm achieving A greater than B in terms of A1 B1 bar plus A0 B1 bar into X1, right? So then, similarly, how we got the A greater than B? So the same way, we have to draw the K maps based on the conditions. So this is for A is equals to B. So for A is equals to B, this is how you have to consider all ones. 1, 1, 1 and as well as 1. So likewise, we will be observing, or else we get the expression, Boolean expression as A equals to B, X1, X0. And similarly for A less than B. So for A less than B, 1, 2, 3, 4, 5, 6. So 6. Out of 6 combinations based on the K maps, I'm getting 1 quad, right? I'm getting 1 quad and then I'm getting 1 pair, 2 pairs, right? So 2 pairs and 1 quad. So this is what the expression I got for A less than B, and this is the expression I got for A equals to B, and this is the expression I got for A greater than B, right? So after modifying the K map, or else after drawing the K map, the second thing is to write the circuit diagram, right? So this is just a circuit diagram. This is not the truth table. So this is a circuit diagram, where in the circuit diagram, what am I doing is I'm just drawing the circuit diagram based on the expressions, right? So based on the expressions. So here, A greater than B, A equals to B and A less than B. So these are my inputs. A1, A0, B1 and B0. So for each A1 and A0, I'm connecting it with a NOT gate as well. Okay, why? Because here in the expressions, I got like A0 bar, right? Complementary. A1 bar, B1 plus A0 bar, B0 into X1. So obviously, I have to consider the NOT gates. And then after drawing, that means for each and everything, A1, A1 complement, A0, A0 complement, B1, B1 complement, and B0, B0 complement. So after this, what am I doing is, as per the expression, okay, as per this expression, A less than B, as per expressions A equals to B and A less than B, the connecting part has to be done. So here, if you observe, the connecting of A greater than A, this is about A less than B, right? So A less than B is this one, A1 bar B1 plus A0 bar B0. So A1 bar B1, A1 bar B1 plus A0 bar B0, A0 bar B0. Okay, right? B0. So here A1 bar. So this is A1 bar, right? So this is a A1 bar, and then this is a B. Then B1 bar. So this is a B1 bar. A1 bar B plus A0 bar. Sorry, A1 bar B plus A0 bar is connected, and then B0. So after this, what am I doing is A less than B. So this using this expression, I am able to draw the circuit. So here, if you see A0 bar B0, right? So A0 bar B0, this is B1 connected, and then B0 as well connected. So here, if you observe, totally how many AND gates? 1, 2, 3 AND gates. So 3 AND gates and 1 OR gate. So totally 3 AND gates and 1 OR gate. And here also 2 XOR gates, right? So here X1 and X0. So here 2 XOR gates with respect to 1 AND gate. Okay, that is for A is equals to B. And then for A greater than B, here we see the 3 AND gates, right? So these are the 3 AND gates. So this is the 3 AND gates, and here 1 OR gate. Okay, based on the expressions, this is how we can draw the circuit diagram. And then finally, coming to the applications. So applications are comparators. They are used in the central processing units and as well as the microcontrollers as well. And then these are used in control applications, which binary numbers representing physical variables such as temperature, position, etc. and compared with reference value. So most of the comparing devices, such as, if you want to compare the temperature, or if you want to compare the pressure, such kind of devices, we can easily make use of this comparators. And as also the comparators are also used as process controller and for servo motor controller. So here the comparators, they can also be used as the process controller and also the servo motor controller, and then used in password verification and biometric applications as well. So these are the few applications where we can make use of this comparators, and there is a password verification as well, and as well as the biometric applications. So this is about comparator. How, in order to design a comparator, what sort of steps that we can take. Okay, not only the comparator, if you want to design the encoder, right? If you want to design the encoder, being a designer, always remember that as much as the gates are less, okay, when the when the circuit is examined, or when the circuit is built in a very less complexity, the less complexity is achieved, the more reliability, right? The more reliability is, the greater the reliability. The lesser the complexity, the greater the reliability, right? So this is how we can reduce by using the gate modeling. So remember that not only with the comparators, any sort of circuit that you are considering, first and foremost thing is consider the circuit diagram. Okay, mention the input and output, mention input output things properly, and also do write your code. Okay, do write your code in terms of any sort of modeling styles. In the behavioral modeling, gate level modeling means SN is a keyword, right? So by using the keywords pertaining to that particular modeling styles, you just write your code. Okay, remember when you're writing the code, colons are important, semicolons, colons are very important. And then when you are writing your code, remember that if you are writing a normal code, you have to mention the keywords. Okay, module here I mentioned, and then ending up with the end module. So soon after drawing the circuit diagram, okay, the second step is just draw the truth table. Okay, the truth table based on the conditions that you're considering, the input, the output, what you are observing. Okay, what sort of conditions that you are getting. Okay, it's a true or false. Okay, if it is glowing, it is true. If it is not on the switch, if the switch is off, then it is on off condition. Okay, so after the circuit diagram, so obviously we have to move with the truth table, and from the truth table, in order to minimize the gates, okay, minimizing the gate is one of the advantageous thing that we have to achieve, right? So in order to minimize the gate, the third most thing that we have to do is drawing the Karnaugh maps. Okay, so when you draw the Karnaugh maps can be drawn with the help of the truth table. Okay, only with the help of the truth table, the Karnaugh maps have been drawn, and from the Karnaugh maps, the Boolean expressions have been observed. Okay, first is all about the circuit diagram, and then second one is about the truth table, and the third one is about the K maps. Okay, the K maps, and the fourth thing is the expression, and from the expression we can draw the gates. Okay, we can draw the circuit, we can draw the diagram as well in terms of the gates. That's a final thing. Okay, extracting the diagram. So here remember that from this circuit diagram, truth table is been evolved, and from the truth table, Karnaugh maps we are moving on. So based on the Karnaugh maps here, at these situations we can reduce the number of gates. That means what? The 100 gates can be reduced to 50 or 40. That is one of the greatest thing that we can do with the help of this Karnaugh maps. And then after K maps, the expressions is evolved. Okay, the expressions are obtained from the Karnaugh maps. So in the expressions, you can draw the circuit diagram as well based on the expressions. So in the expression, sum of the products and product of sums, right? So from the expressions, by using the OR gates and the AND gates and NOT gates, whatever the gates based on these expressions can be drawn within the circuit diagram. And then this is the last stage of each and every module that you are going to design. Okay, so after designing, you have to sum up with the applications. Okay, where you are going to use this product, where you are going to implement this the design product, where you are going to apply this. Okay, all such things you have to ponder, and you have to write each and everything very clearly. So for example, here comparators, as these are the comparators, we are using that at different levels. Okay, in the reality, in order to compare the temperature, in order to compare the pressure, okay, in order to compare the time delays, in order to compare the event controls, we are using this comparator devices in the real-time applications. And also, what we're saying is for the biometric applications. See, these are very innovative, right? So these applications, this sort of applications are very different when you compare the real-time applications in the real-time applications. So you have to mention each and every application clearly, and then finally you have to conclude regarding the circuit. So this is how we can solve, or else in order to reduce the complexity, the best way is to minimize the gates. So the best way is to minimize the gate can be achieved only by using the coordinate maps. Okay, this is how we can solve the problem. The complexity can be easily solved. So this is all about an example based on the gate level modeling. The problem, how can we solve in the gate level modeling? Okay, I hope you all get the point. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.